Come on everybody, welcome back to this workshop, and today we're going to talk about the forward process. It's the first step of our hybrid approach we're working on. So let's jump right into it just after the intro. See you guys. Is this one. So we want to solve this, okay, with a hybrid process. And in the first video of this workshop I told you that what we call a hybrid process is just the combination of a forward modeling of this one with inverse modeling. The forward step is just about to take this one and obtain some value of the temperature at some point in the body you're studying, okay? And the inverse model is just to take those outputs, those temperature at each point, and try to come out with the temperature on each other points. So if you want more explanation about that, I want you to go straight to the first tutorial of this workshop. You will have all the explanation you need to know, you need to know about what we are doing right now. So it's simple. Today we're gonna use some numerical approximation of this type of derivative, and the one we're gonna use here is the Taylor approximation. So we want to change this into something with t with respect to e plus 1 and e minus 1. So let's say what I'm talking about is this. I want to insert a formula, and the one I would like to insert here is, you have first of all the partial derivative. So partial, what is that? Oh, forget about this partial. Is it this or this? Okay. Seems weird, but it's okay. Partial of t over the partial of x to 2, and we say this is equal to, or must be equal to, the, so just say equal to, in a real case they are not equal though, so don't take both of them as their equal value. No, one is an approximation of the other. So what we're going to type here is the approximation of the first member of this equation. So it's equal to let's say t with respect to e plus 1. No, at e plus 1, sorry. T at e plus 1 minus 2 at e plus t at e minus 1. That's it. Over so I hope can say delta. No. And what if I want to add something like let's try to found that symbol here. No, this is Navla. So let's see for example empty. No, not here. What if I want to have the symbol? This is the one I'm looking for. Okay. Delta X to the 2. Yeah. This is the approximation I'm gonna use on this step. It's easy to use and easy to understand. Really easy to understand. So now that I have this, what I need to do is to run this equation at each node. Let me draw the body we're starting right now, so just to make things clear about what we are doing right now. So let's say I want to insert something like a frame. No, yeah, a frame. Yeah. So let's say for example we have this body here. Okay. So let's change some little stuff here. No. Matthew. No. I want something else. Something like choice. Okay, it's okay. Let's change this. I wanted to have something else, something different, something with maybe for example yeah, something like this for example. Okay. It's not really let's say yes, let's say this. Okay, so this is the body we're starting, and when I talk about nodes, I mean when I talk about compute value of the temperature at each node, I'm talking about something like this. Let's say for example we have this line or this axis, and on this axis we have it had some nodes on it. So insert frame, and let's say cycle, and let's draw a little one here. Okay, so copy and paste 1, then paste 2, then paste 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we have this. So let me just what I want is to reduce. Oh, it's reducing. Okay, let's say this is what we have, and what I'm talking about is that at each of this point I want the value of the temperature. Okay, and to have that value I'm going to use this equation, and what we have to do right now is to replace this into this first equation, and try to compute, no, not try, and compute to obtain the value of the temperature at each node at each I. So let's make this quick. The equation we want is something like this. So we first have at this node, for example, this one, if this one is the node number 1 or the position 1, this position 2, position 3, and this the position 10. So at this position, what we have is t at 2 minus 2t at 1 plus 2t at 0, and t at 0 is this value here. It's a boundary condition, so it's the value at the boundary of the boundaries, this boundary, not this one. This one is t at the point n plus 1. So what we should have right now is I'm just gonna type them one after another. So we have the open braces and say into it. Let's type something like t at 2 minus 2t at 1 plus t at 0. Yeah, and this one is over and this one is over delta x at to the 2. Yeah, so this one is equal to k. So we're gonna make this for at the position 1, at the position 2, at position 3 till the position 10, and obtain something like 10 value of t, and we're gonna use linear algebra to solve the problem. So we have this first equation. Let me just copy this because I'm going to use it for the other one. So this is so finally we have this. So at a equal to 1, a equal to 2 until till a equal to n plus 1. So we have this. So the thing we have to talk about right now is the boundaries condition. So there are several type of boundaries conditions. So what we call boundaries condition is just the state of the temperature on this side of the boundaries and this side of the boundaries, and also maybe this one up here and this one here. But because we are working on one-dimensional equation, we just need to know the value of the temperature here and here. So let's say, for example, on this side we're going to set the value equals to, let's add a text here. For example, the value equals to 25, for example. So let's drop it here, and on the other side, so the other one right here, let's set the value to, for example, 0. This is just an example. It's important, we need those values because we need those values, okay? Because just take a look on this. when we look up these equations, so let's say this is the value here, this one is the value here, this one is the value here, and we're going to walk straight to the line and step here. This will be t at the position 10. So we want to know the temperature on these points, but we want to know these values according to this one, which is t at 0, and this one, which is t at the position n+1. So we want to know the value on these points with respect to the value on this point and this one. So this is why those values are important. Most of the time you're gonna have this type of boundaries condition, but sometimes you also have initial value. So maybe the temperature at a t right there will be with I mean the time variable, so the time direction, we're not using that one right here. So here we're just working into the space dimension. So we just have a one-dimensional equation into the space, and we need this value and this value. We don't need initial value here because we don't have t. Forget these values and this value, sorry, and this value. So it's important. So in the second part of this tutorial, we're gonna implement this equation into Scilab to come out with the value of the temperature at these points. Okay, so see you guys next in the second part of this tutorial.